My name is Luisa Semeska, and I'm a staff scientist here at CHESS. FMB stands for the Functional Materials Beamline, and when we talk about functional materials, we're talking about things that have interesting non-mechanical properties, so things like semiconductors or nanoparticles. In reality, at FMB, the distinction between functional and structural materials that we study is a little bit more soft. We actually study a lot of structural materials here at FMB. In particular, we tend to look at lighter weight materials that are more compatible with the energies we have here and not with our sister beamline at SMB, where they study heavier things like metals. So FMB is part of MSNC, which is funded by the Air Force. The Air Force Research Lab is really interested in next generation materials, both in discovering those new materials and translating new materials into industrial processes. And we do that by characterizing materials at the microscale and at the macro scale, from millimeters to even greater length scales. When I think about the capabilities at FMB, I think about flexibility. We have kind of 4 areas that I consider really flexible and kind of are what make the beamline unique. And those are the energies. We've got 4 different energies, and we can hop between them kind of at will. This is distinct to a lot of the other beamlines where changing energy is kind of a big task. We have really flexible optics, so we can go between having a big beam that's 2 by 2 millimeters down to a focus beam of just a couple of microns. So that allows us a lot of flexibility in how big a piece of the sample we illuminate. We have a really flexible sample area, so we can have users who bring in really complicated in situ setups, and we can build up everything to lasers and robot arms all the way down to micro focus sample stages. And then the last piece that is really flexible is the detector table. So we can use that to change between our different experiment modes. And so the kind of the 2 main experiment modes that we have at FMB are imaging, and that's similar to what you'd imagine for radiography at a dentist or at the doctor. So there you're taking your big beam, your 2 by 2 millimeter beam, and you're taking movies of dynamic processes, or you're taking computed tomography, so 3D reconstructions of objects. So that's one mode that we have. The other mode that we have is a scattering mode, and that's typically we do simultaneous wide and small angle scattering, so simultaneous wax and sax, or sax wax, people say both. The idea there is that the scattering is going to tell you about the length scales in your sample. So wide angle scattering will tell you about the really small length scales, so interatomic spacings. It helps you understand crystalline materials. And then the small angle scattering tells you about the larger distances in your sample. And that's useful when you have things that aren't quite as crystalline, like the polymers and composites that we look at here at FMB quite a lot. Everyone's probably familiar with the concept of 3D printing or additive manufacturing, where you kind of print one line of material and go back and forth, and you can build up a complicated part. The properties of those things are maybe not so important if you're just printing a toy, but they're really important, and the reliability of those parts is really important if you're doing something like driving a car or putting it in an airplane. Our role at FMB in understanding 3D printing is to look at both the in situ processes as they're happening on the beamline, or we can look at ex situ parts that have already been printed, and we can characterize those and look at their structural properties. Right. So I also mentioned that AFRL is really interested in discovering new materials, and so one piece of what we do at FMB is support groups who are interested in automating materials discovery, and they do this in numerous ways. We've had groups bring solution mixing robots to the beamline, where they've actually combined different solutions and looked at their properties kind of as they're being created. We've also had groups bring a complicated kind of laser annealing setup. So they've got a wafer with a bunch of different oxide materials on it, and they're actually annealing those oxides in situ and looking at the diffraction patterns to know what crystalline phases are present. And the goal of that experiment is to actually have a computer across campus decide where to look on the wafer for the next compositions and decide what annealing conditions to use to explore the wafer and basically come up with new phase diagrams. So that's really exciting work. So remote access has been going really well, and one of the reasons it's been so successful is that our standard SAX wax mode that I mentioned is really compatible with remote and kind of mail-in operation. So we've designed these special sample holders. We can send them to users, they can fill them with their samples and send them back to us, and it's really easy for anybody to just attach this sample holder to the right mount and pop it on the beamline. It goes into place with a kinematic mount, so we know exactly where it's going to be. It's going to wind up in the same place every time. You don't have to have special training to mount the samples or to prepare them in your lab to put them on the beamline. So that has worked out really well. Not only can the user log into the station computer to collect data, but they can actually also log into our analysis computer at the same time. And so they can be collecting data and running scans and also looking at the process data as it's being collected, almost as if they're sitting right here at the beamline. Right, so I talked a lot about the Air Force Research Lab and our collaborations with DoD, but a lot of these research questions that we're studying, particularly with the 3D printing of lighter weight materials, are really relevant to everybody. And you can imagine that lighter weight components for aircraft are not only valuable to the Air Force, but would also be valuable for commercial airlines, particularly through the avenue of reducing fuel use or improving fuel efficiency by having lighter weight components. So you can also think about the ease of manufacturing. If it's possible to make components, replacement components for aircraft while they are away from a base, so maybe somewhere at sea, or maybe we're talking about like spacecraft, maybe you're printing parts in a space station, you need to be able to do so reliably and consistently. So I think that's really cool. Yeah. Yeah, so we're a pretty brand new beamline. We're only, I guess, 1.5 years old at this point. And so there's a lot of areas that we're still growing into. And the main areas that I'm thinking about are, improvements that we can make to the techniques and improvements that we can make to access to those techniques, and also expanding our user base in AFRL and DoD and the related manufacturers. Most of our efforts over the past 1.5 years have been towards really improving our techniques and making them excellent. And now the next step is to make them even easier to use. I think our biggest efforts now are going to be towards streamlining transitions between all these different flexible components. And we've already made some improvements, like being able to translate our detector table from side to side. So now switching between SAX wax and 2D imaging is a simple one motor move. The entire table slides over and you can have your in situ setup right there on the table in the same place. The beam is in the same place, and all you've done is change the experiment around it. So there's a lot more, there are other things like that we'd like to implement, like improving our camera views of the sample, which will also help people who are operating remotely and things like that. But yeah, we're sort of shifting from technical improvements to ease of access. So one of my favorite parts about working with AFRL and all of the chess researchers that are part of the team is that it is such a great team. Everybody's really invested in solving these materials problems, and we work together really well. And it's a really collegial environment, and the people are terrific. Yeah.
My name is Aaron Finke, and I am the staff scientist for the Flex Beamline at Chess. And so my primary role is to assist users who use our Beamline for experiments, and I also head up a research project for special experiments in protein crystallography. Flex stands for Flexible Beamline in Macromolecular Crystallography. So not flexible as in bendy, but rather flexible as in we can accommodate a large and wide variety of experiments related to crystallography. And so what we do here is we try our best to accommodate difficult experiments that would be difficult to perform at other beamlines in the country. So Flex's main area of research is in structural biology and molecular biology. And so what we're looking at here and what our users are looking at here is the atomic structure of proteins, nucleic acids, and complexes that contain the two. This is really important because the more that we understand about the atomic structure of proteins and nucleic acids, the better that we understand their function, because of the way that proteins interact and fold upon themselves gives us a very clear depiction of the way that they interact with other proteins, with molecules such as drug molecules, and the way that they function in their particular biological site. So Flex is dedicated to crystallography, in particular protein and nucleic acid, biological macromolecular crystallography. And so we can perform just about any crystallographic experiment. So our beamline is fed by an undulator-fed source, and so that delivers intense X-ray beams of a beam size ranging anywhere from 100 microns down to 10 microns in size. And we have a specialized optical setup that allows us to deliver even more X-rays to the sample by sacrificing a little bit of the bandwidth of energies that we use. And so we can accommodate a number of different crystallographic experiments ranging from standard crystallography at 100 Kelvin up to new and unusual experiments that including room temperature crystallography, serial crystallography, and also crystallography at high pressures. So Flex has three main research thrusts and three main experimental types that we kind of focus on. While we're really flexible and we can accommodate a large number of different experiments for different users, most of the experiments fall into three categories. The first is standard crystallography at 100 Kelvin, using protein crystals that have been frozen or cryo-cooled rather in liquid nitrogen. That's what we call standard crystallography or standard cryocrystallography. The second is room temperature crystallography, which requires a bit more delicate handling of protein crystals. As the name implies, these are done at room temperature, and so this includes techniques such as doing single crystallography, using very high scan rates, and also serial crystallography, which uses a large number of crystals, and we collect very small data sets from each crystal and then merge it all together. The third one is high-pressure crystallography using a diamond anvil cell. This is headed up by my colleague Zhangmu Wang, and so he heads up this experiment in which two diamond anvil cells provide a large amount of pressure to a protein crystal to simulate pressures that you would find at the bottom of the ocean, for example. So what our users do is they will grow crystals of proteins and nucleic acids that they're interested in studying, and they'll bring them to the beamline. So the crystals are held in place in front of the X-ray beam with using a sample stage called a goniometer, which holds the sample in place and rotates it while exposing the crystal to the X-ray beam. X-rays will diffract off of the crystal, and then those diffracted X-rays are recorded on a large area X-ray detector. And then using some mathematical trickery, you can back calculate the atomic structure of the crystal that diffracted the X-rays in the first place. So after Cornell was closed last year for the pandemic, Chess got special permission to reopen to do some COVID-related research. And so in collaboration with Rick Sirione in the chemistry and biochemistry department, we were looking at a class of enzymes that is relevant to the development of drugs for COVID treatment. A class of enzymes called glutaminases. And so Professor Sirione is a cancer biologist, but as it turns out, this glutaminase enzyme is also a potential drug target for COVID as well, because the biological pathways that for the COVID virus also rely heavily on this glutaminase enzyme. And so in collaboration with them, we did some room temperature crystallography experiments to understand the difference between two drugs that, when we did a crystallography experiment at low temperatures, these two drugs interacted with the glutaminase enzyme in exactly the same way. There was no fundamental difference between the two, which is very strange because these two drugs had orders of magnitude difference in efficacy in inhibiting this glutaminase enzyme. And so we did room temperature crystallography to better understand what exactly was going on and why the drug efficacies were so different between these two molecules. And we were able to determine a difference, but we only ever saw it at room temperature. So here at MacChess, at the macromolecular crystallography Beamlines, we were actually the first to do remote data collection here. So we've been doing remote data collection for users for the better part of a decade now. And it's a very popular option for many of our users, even before COVID, because of the convenience of it. Before COVID, I would say approximately half of our user base was collecting data remotely, and now post-COVID, nearly all of our users do. So we make it as simple as possible for users to collect data remotely by giving them complete control of the data collection desktop. So users will send in their samples frozen in liquid nitrogen, and then we have a robot auto mounter that picks up each individual sample and then puts it directly onto the goniometer for analysis. And so there's no human intervention required for users to collect data at the Beamline remotely. So remote data collection at Flex has not changed since before the pandemic. So users collect data the same way that they did before remotely. What has changed is that we've implemented a number of communication tools to streamline communication with our remote users using a combination of Zoom, Slack, and the reach ticket system to reach the chess operators at any given time. And so they have 24-hour access to chess operators still. Yeah, so the research that goes on at Flex has broad-reaching implications for society as a whole, because what we study here is biology at the molecular level, and because biological structure implies function of the biological system that's being studied, this has a number of implications, especially in things like drug development. So the better that we understand the three-dimensional structure of proteins, enzymes, and complexes, the better that we can develop drugs and medications to help inhibit or promote certain enzymatic pathways for health-related reasons. And so any sort of medication, drug development, pharmaceutical development, all relies on crystallography to better understand the systems that they want to try to inhibit or promote. We have a number of exciting upgrades happening right now at Flex. In particular, we are implementing some new software and data collection GUIs that will streamline data collection and implement some exciting new features for users. In particular, the ability to raster across large crystals and find the best spot for getting the best diffraction information out of a single crystal. Also, developing new technologies and new experimental setups for doing room temperature crystallography and also for high pressure crystallography. So we've just started accepting users for doing protein crystallography under high pressures. And so the way that that works is a protein crystal is loaded in between two what are called diamond anvil cells, which are two pieces of diamond that are cut in such a way that they are sandwiched together to increase the pressure of whatever is in between them to extremely high and consistent pressures, similar to what you can see at the pressures that are at the bottom of the ocean. And so this has important implications for understanding structural biology at the bottom of the ocean, where the majority of the world's biomass actually exists. My favorite thing about working with the users of Flex is that I get to see, I get a bird's eye view of the different research projects that people are working on and the challenges that are associated with the latest and greatest research in structural biology. And so it's very exciting to see not only where structural biology is headed in the next few years, but also how I can help assist with new experiments, new technologies, and new ideas.
I'm Kate Shanks. I'm the staff scientist at the FAST Beamline at Chex. FAST stands for Forming and Shaping Technology, and that refers to the science mission of the Beamline, which is to investigate and understand and solve performance and processing issues in the field of structural materials. FAST focuses on sort of high energy, monochromatic techniques in both diffraction and imaging. And in particular, applying those ways of probing specimens to kind of in situ sample environments so that we can investigate the microstructure of materials while they are being mechanically loaded, while they're being thermally cycled, and also in kind of more high-speed, time-resolved ways as materials are actually being processed or even built up in like a 3D printing architecture. We primarily look at, as I said, structural materials, which is a term that refers to kind of largely engineering materials, so things like cements, ceramics, various metal alloys that are used in applications where their purpose is to bear some kind of mechanical load. So that's in contrast to what some people might refer to as like a functional material, which is more, we're interested in those for like their electrical properties or their magnetic properties. Here, we're primarily looking at things that are of interest for their mechanical properties. And the goal is to build an understanding of how the microstructure of the specimen relates to its mechanical properties. So things like its strength, its brittleness versus ductility, and in particular, one big question is how do materials fail? So what happens to the microstructure when the material cracks or gets crushed or gets pulled apart, things like that. An example of an experiment like that we did this past fall that I thought was especially fun was looking at the mechanical properties of basically moon cement, so a cement made of moon rocks. And so the idea behind that is that if we, as like a civilization, ever want to start building infrastructure on the moon or in space, we are not going to want to carry all of our construction materials up from Earth with us because that would be prohibitively heavy. We would instead want to be able to make things like cement out of raw materials on, say, the moon, if we were going to try to build a research station there or colonize it or what have you. But before we do that, we would want to know, how does moon cement compare to Earth cement in terms of its mechanical properties and loading behavior? So this was with researchers at Penn State, and they had not literal moon rocks, but cement made with a lunar regolith simulant. So that's a synthetic material that is made to mimic the composition and properties of rocks found on the moon. So they made cement out of this simulant material, and we put it in our RAMS load frame and watched its microstructure evolve as it was crushed. Up and coming experiments that I'm really excited about developing are in situ time resolved studies of additive manufacturing processes for metals. So additive manufacturing, kind of AKA 3D printing, is like kind of an exciting developing alternative to traditional machining, and having kind of robust, reliable, and well understood additive manufacturing techniques for metal alloys would open up a lot of new opportunities and kind of ways to build engineering components. So like stuff for airplanes, stuff for machining, stuff for medical devices. It potentially lets you make things maybe cheaper, lets you make unique components on the fly just by loading up, a CAD drawing into your 3D printer and pushing go, as opposed to having to have an entire supply chain and machining line already set up to, do traditional machining to make specific components. However, we need to understand the kind of microstructure and composition of metallic alloys that are made via 3D printing, because they're very different than things made via conventional machining techniques. So at FAST, we have high enough energy X-rays and bright enough X-rays, and we are starting to have fast enough detectors to put an additive manufacturing chamber into the beamline and watch in real time as a part is built up through like laser heating of metal powders and things of that nature. And we can see how the microstructure evolves in the kind of millisecond, potentially down into the nanosecond regime. Yeah, so remote access is actually going extremely well. I was thinking about this, and I think for a lot of us in the Synchrotron community, the experience of sort of being at the beamline is like such a unique experience, and it's so immersive. And honestly, it's really fun that a lot of us maybe had trouble in imagining like replacing that or replicating it with anything other than a group, coming here and sitting at the beamline. But remote access, I think, has succeeded in doing that. And I see that in the user groups I've been working with, who keep saying, like, oh, I was kind of skeptical about this, but it's like we're at the beamline. And so that feels like a big success. And that's completely to the credit of the kind of class IT staff and operational staff that has made remote access run really smoothly. And it's a really good approximation of being here. Parts that go into airplanes, parts that go into medical devices, building materials, all these kind of things that impact our daily lives in many different ways. We'll be able to do all of that better if we know how to tell when a part is going to fail, and if we know how to make kind of better, more durable, longer lasting parts more cheaply, kind of more effectively. And if we can start building more predictive models for material performance, that will go a long way to making better engineering components for our buildings and planes and infrastructure. So it's kind of like corny to say this as an X-ray scientist, but literally the future at FAST looks brighter. So in the coming year, we're looking at upgrades to the upstream optics that will give us a brighter monochromatic beam, which will enable more time-resolved studies of materials processing and just more in situ, more time-resolved, more realistic conditions for how these materials actually behave in their real-world applications. There was a professor I had for physics when I was in college who used to say, you can't be a scientist by yourself. And I think there's a lot of truth in that. And so from that perspective, I really love working as a part of a big team, getting to work with all these different user groups. There's always kind of something new to learn or something new to try. And you get to do those things with experts, and that is just a fantastic place to work.
My name is Chris Pollock, and I'm the staff scientist at the Pipox Beamline at Chess. My role is to help users both plan and conduct their experiments, and also to process, analyze, and interpret the data that they get from those experiments. So Pipox stands for the Photon In, Photon Out X-ray spectroscopy beamline. And as you might be able to guess from that name, what we focus on at Pipox is studying interesting chemical systems using X-ray spectroscopy. So what I mean by that is we generally take a sample and we hit it with high energy X-ray photons. And in one flavor of X-ray spectroscopy called X-ray absorption spectroscopy, what we do is we look at the energies that that sample absorbs when we hit it with X-ray photons. From that, we can learn things about what the geometry is of that atom that's absorbing, what its oxidation state is, and also how long its chemical bonds are. Now, from the name, X-ray absorption, that's the photon-in aspect of Pipox. Another flavor of X-ray spectroscopy is called X-ray emission spectroscopy. And what that involves is once we've excited those electrons in the sample, if you wait a little bit, the sample will then give off or emit X-rays of different energies. And so if we look at the energies of those X-rays that get emitted, we can learn different things about the sample that we have in the beam. We can learn things like how many ligands are bonded to that atom, what are their identity, and what is the spin state of the atom that's absorbed those photons. Now, from the name there, it's X-ray emission. That's the photon out aspect of Pipox. So together we have the photon in, photon out, X-ray spectroscopy beamline. The main goal of the Pipox beamline is to investigate chemical catalysts. And so a catalyst is a chemical species that speeds up a chemical reaction without being consumed in that reaction. As you might imagine, catalysts are quite common both in nature and also in man-made processes. So they're involved in everything from synthesizing DNA in your cells to producing industrial fertilizer that helps to feed billions of people. So they're very useful substances. But unfortunately, in a lot of cases, we don't really know how they work on a molecular level. And that poses a problem because if you ever want to improve how a catalyst works or design a new one, you really need to know how the existing ones function in order to design better ones from that. And so that's where Pipox comes in. Our goal is to be able to study chemical catalysts, ideally under operating conditions, so that we know how they function, how their structures might change during a chemical reaction, so that we can then learn from that and design new and better catalysts from what we currently have. As I said, catalysts are involved in all kinds of different processes. And so when we designed the Pipox beamline, we really had to make that a very flexible end station, since you have to be able to look at everything from heterogeneous catalysts, like on industrial scales, all the way down to the enzymes in your cells. So we have the ability to look at a wide variety of elements in a wide variety of environments to answer a wide variety of chemical questions. The Pipox beamline was designed to be able to look at a wide variety of samples in a wide variety of different environments. And so that flexibility comes from really a number of different factors that we've built in. The first is the energy range that we can use to hit our samples with. So we can reach elements all the way from calcium all the way down to uranium. So almost the entire periodic table is accessible to us. We also have the ability to look at a wide variety of environments. So that could be samples that are a liquid in solution, or it could be an electrochemical cell that has applied voltage, or it could be a frozen sample that's at 10 degrees Kelvin. So the environment that the sample is in really doesn't limit what we can look at. Another thing that we have that a lot of beamlines don't necessarily is we have access to several different spectrometers that let us do techniques that you can't necessarily do with all other beamlines. Some of these spectrometers are unique only to chess. So we can do both X-ray absorption, X-ray emission, and we can also combine those techniques into more complicated two-dimensional methods so that we can really tailor the experiment to help the user answer whatever chemical question they have in the best way that they can. And the last thing that we can tune is we can tune the size of our beam. So we can tune all the way from about a 1 by 2 millimeter beam, so a very big beam, to hit if you have a very big sample, or we can focus that down to about 100 by 200 microns. If you have a small sample or you get a very high flux density, we can tune that as well. Some of the really interesting experiments we've done lately are looking at electrochemical materials. So these could be things that you put into a battery or a fuel cell, and when you either store or release charge, they undergo some kind of a chemical reaction. And in a lot of cases, the people who make these materials don't necessarily know what the chemistry is that's happening in them. So you often have many different metals, some nonmetals, and when you charge and discharge, we don't really know where that charge goes. Using X-ray absorption and emission spectroscopy, though, you can monitor the oxidation states of the different elements in those samples, and because these are inherently element selective, you can look at each one sequentially, and you can see where the charge is coming from and going to as the material goes through its charge and discharge cycles. So you can really learn information that is difficult or impossible to learn without using these X-ray tools. Remote access has actually been going really well at Pipox. So thanks to a really dedicated effort by the IT and technical staff at Chess, we've managed to get the beamline into a state where a user can sit at home and they can log into the station computer and they can see and control just about everything that they could if they were sitting here physically at the station. And our users have actually been really enthusiastic about trying this out. So we've had samples come from as far away as Germany for them to be able to do these remote experiments. And because of that, we really have been able to keep doing exciting science even while we have these restrictions in place because of COVID. And looking forward, I think that particularly for new user groups, the ability to do remote experiments really lowers the barrier to doing synchrotron experiments. And so even once the restrictions from COVID are lifted, I think remote operations will remain an important part of our user program simply because they allow more people to do these experiments that wouldn't necessarily be able to. Because we investigate such a wide range of systems at Pipox, there's really a number of ways that this Beamlines research can have a broader impact on society. Probably the most obvious one would be on the energy economy. So we have a lot of research that goes into electrochemical systems, fuel cells, batteries, different electrochemical catalysis. And so what this research can do is it can change the way that we both generate and store electrical power, can make those processes more efficient. There's also research going on that could change the types of materials involved in these systems. So right now they use a lot of both precious and expensive metals and also some hazardous materials. And so with the research that we're doing, we're hoping to be able to replace those with more abundant, cheaper, and more environmentally friendly materials. So if that research comes to fruition, it can have a big impact on how we use energy as a society. We also do quite a bit of research on biological systems, looking at how enzymes function. And so this can have impacts both on just fundamental knowledge, knowing how nature carries out chemical reactions, to drug design, because if you know how enzymes function, you can potentially design drugs to target those enzymes. And also, a lot of these enzymes in nature do very complex, challenging chemical reactions, things that we can't currently do in the lab. And so chemists can then use what we learned about those catalysts as inspiration to design catalysts that can do those challenging transformations in the lab to mimic what nature does. We're always trying to adapt and approach new problems and new challenges at Pipox. So right now we're involved in designing a couple new sample environments. So we have one that will enable us much better temperature control over our samples. And we have another one that will enable us to look at heterogeneous catalysts as they do their chemical reactions, which is something we can't currently do. We also are working on a project that will change the way that we do energy scans at the Beamline. So right now it takes us maybe 5-10 minutes to do an energy scan. With this new technology implemented, we'll be able to cut that down to about 30 seconds. So it will save our users quite a lot of time, and we'll be able to do experiments that we just frankly don't have time to do anymore. Those are kind of the big projects that are in flight, and we're pretty much always just trying to push the envelope in terms of how low of a concentration can we measure, how quickly can we scan, and how low of a signal can we actually measure. So we're constantly trying to push the boundaries of what's possible. My favorite thing about working at the Chex Beamline is the diversity of science I get to be a part of. So because this is such a flexible beamline, I'm always encountering new challenges and new problems and new science. So 1 week I could be working on a metalloenzyme, the next I could be working with the user on a fuel cell component, and the next I could be looking at a small molecule catalyst. So there's always something new, there's always something exciting going on, and I'm always learning new things at this beamline. So it's a fun place to be doing science.